Okay, welcome back to another edition of our project to build an XLR to USB converter. Um, in today's episode, what we're going to talk a little bit about is different kinds of capacitors. We built several capacitors before. We didn't really talk too terribly much about them. So to finish up that round of stuff, we're just going to quickly go through a couple of different kinds of capacitors before we actually build them. So um, the capacitors we built last time were known as multi-layer chip capacitors, right? And there's a ceramic capacitors, and this particular vendor has a nice selector guide that's kind of got all the features out there, whether you go to use TDKs or not. For the most part, I consider most of these capacitors kind of commodity, so there's lots of different vendors, and you just kind of follow the cheap one on DigiKey. So the real important part when you're picking a capacitor is usually whether it's polarized or non-polarized. Obviously, its capacitance value, its working voltage. Those are kind of par for the course. What's a little less obvious the first time you work with these is the effect of different dielectrics, right? And the dielectric is the medium in between the two conductors of a capacitor, whether it's ceramic or whatever, right? So ceramic is a type of dielectric. However, in between, there is several different kinds of products that you can use. All right. For multi-layer chip capacitors, which is one type of non-polarized ones, there's subclasses within there that actually have different types of dielectrics, and that's what this is here. This table is right here. And so, what happens with ceramic capacitors? They don't tend to age too terribly badly. They have pretty long shelf life and things like that, and they're very stable over time. However, they do have temperature coefficients. And so the temperature coefficient is really what sort of separates different kinds of dielectric. And you can see CH, which is not one that I see a whole lot, but C0G, which is also known as NP0, has kind of the best one, right? Its temperature coefficient in terms of the amount change in capacitance over temperature is very, very low, right? It's in parts per million. Compare or contrast that with X7S or even an even higher Temco value like Y5V, and you see that this thing can shift by 22% over its entire range. So C0G has a specced out temperature coefficient, while the rest of them have basically have ranges that they'll just stay at, but they don't really have a prescribed temperature coefficient, and that does turn into costs, right? So that's one of the reasons why you may pick a ceramic capacitor over or a particular type of ceramic capacitor over over another one. And you notice a cost difference in between there. These are considerably more expensive. None of them are out of the range of possibilities. They're still in the few pennies type of range, or 5, 10, 15 cents type of range, until you get into some really high values and stuff. So these are still cheap parts. But if you're doing mass production, and the question was, why should I use NP0, which is usually what I call them, or C0G is a little more standard term, versus X7R, X7S, and then Y5V, which is kind of probably the cheapest ones that you'll see. And the answer is really how well does it track over temperature. And you can see that a 22% change in temperature may mean the difference between a stable oscillator and an unstable oscillator. It may change the frequency at which the oscillation occurs if it's a tuned circuit, like in a radio transmitter or oscillator that's based off of some value. If it's an audio filter, like some of the ones that we'll have a couple of audio filters in here probably, that would change the frequency response to that, and suddenly our fourth order filter that makes a nice anti-aliasing filter and shuts everything down above a certain frequency becomes something that has lots of different individual nodes within it, or individual little little zeros or resonances within it, and suddenly it doesn't look like a filter. It looks like a bunch of little mountaintops or something like that. Right? We did talk a little bit about voltage, and this has a lot more information that's detailing which size go to which. Another factor that's not in this data sheet is the effective series resistance and the stray inductance, and those are really a little bit more about either really high impedance circuits, or like if you wanted to build a capacitor that was holding a charge for several minutes or something like that, then that leakage might become important. So leakage resistance, effective series resistance, and then as you get into microwave or high frequency radio designs, the stray inductance can be there. And hopefully I'll put together something on using LT Spice as a tool to kind of model some of those neat effects. We might see that a little later on, stuff like that. So again, the dielectrics are about its temperature tolerance. You see that there's another table up here that's the capacitor tolerance, and that's actually what you get out of the factory. It's not how it tracks over temperature, it's how you know, these things are fabricated, and there are error tolerances in the manufacturing process. So the fact that two things have the same temperature coefficient doesn't necessarily mean that they came out of the bin with the exact value. And usually this is more about how the manufacturer picks them out of the bin. Sometimes they spend a little more time on processing, but more often they go to a more sensitive machine to grade them out and say that is a 33 picofarad capacitor and that's a 30 picofarad capacitor. You know, that could be a 10% tolerance type of thing, and those two can roughly be about the same in the same bin. You know, so you could get either one. In the meantime, you have much tighter tolerances there, and all that turns into money. So that's multi-layer chip capacitors, right? These brownish looking guys, and that's what we built last time because they have the same footprints as our friendly resistors, other than chip capacitors tend to be quite a bit taller than resistors, right? This is even tall for a resistor. They're usually quite thin, but they have the same footprints, and you would never see a resistor really that tall, or especially this tall, right? So we did talk a little bit already about the different sizes, and to watch out for the inch specification versus the metric specification here, because those are definitely two different things. You know, so just be on the lookout for that kind of stuff. A second type of capacitor class that we would use is the polarized ones, and these generally have much bigger capacitance values. So where you might use these little guys here for bypass capacitors or decoupling capacitors, or even as parts of filters, these guys here we will use quite a bit in power supplies and softening up the power system, and occasionally we'll use them in filters when I need something really big. You can use these in an audio application as part of a filter, like for example DC blocking filters. You generally want capacitors that have really high values, so you're okay with that. So two main types that I use quite a bit are tantalum capacitors and aluminum electrolytic capacitor. This is not a very good picture of it and stuff, but these are the metal can looking ones that you see in a lot of things. And these are quite a bit less expensive, and they're certainly very, very good capacitors. And these are a longer term temperature stable, but they are quite a bit more expensive when you look at them. They have generally have a little bit smaller maximum capacitance range. Like this thing goes only up to 1,000 microfarad, and I'm sure we can get these things into several 100,000 microfarads if we look hard enough. So these are the two data sheets that we will be working with, and it's a toss-up between whether you want to use one or the other. I generally stick with these, but we're going to build parts for them both. So since we already built our multi-layer chip capacitor things, we're not going to use that anymore. And one of the things you might notice about this is that they have narrower pads than their MLCC friends. The MLCCs had the cap going the entire side, which meant that the width of the part was basically the footprint of the SMD pad was a little wider than the part. These generally have narrower footprints. I don't see a picture of it from underneath, but they have kind of a T shape sort of underneath and stuff like that. Yeah, so there's kind of the pad, and sometimes you'll see a little T shape or something like that. Okay, so onto aluminum electrolytics. These have quite a bit different size, although it is fairly standardized. These are the ones that they generally stand up on their edge, and they have this sort of you know, kind of trapezoidal shape type of deal, whatever, chamfered corners. And the chamfered corners will indicate the positive pin. Because these are polarized, as are the tantalum ones, don't put them in backwards. You will cause them to eventually boil and explode, and they build up quite a bit of pressure. I don't know if you necessarily lose an eye, but it certainly scare the hell out of you. So, you know, be aware of polarities and double check again when you do a lot of stuff. So with that, let's get back into Eagle, and we'll begin with the tantalum capacitors. I'm only going to make 2 different sizes. There's a lot of sizes, but I've found that almost all of my work I can do with the size A, and these are not just Chemet codes. These are fairly commonly used. You can still see these designations in the DigiKey. So size A and then size D. And one of the things you notice is that size D, size X, size E are all the same except for they're a little different height. You know, these are the EIA codes, which are metric sizes, just like we had 0402 was a US size, which turned into, I think, 1608. Well, that's 0603 is 1608, you know, etc. So these are EIA codes, and they're basically the metric 2-digit code system plus a height. So that's where that system comes from. I oftentimes will refer to them as size A and B. We're victims of our upbringing, and that's how I started out. So this is going to be a fairly easy job to do here in Eagle, but in the spirit of you know, like I said, this project was going to be about cradle to grave, so we're going to build all the parts, right? So let's get to it. It's going to be a new package, C pole size A. Okay, and let's just put the EIA code right there in there so that we have it in the description. Size A capacitor okay, so there we go, size A, piece of cake. Now we've done this a bajillion times before, and it never gets old, right? The same old, same old, same old. This one's a little nicer because it does actually give you the width. It doesn't give you the actual preferred layout size that I've seen in this particular data sheet, although I may have missed something. I kind of moved through fairly quickly. But what it does is it gives me the actual footprint, foot pad sizes in a nice way, and it's all metric. So let's go ahead and start with 0.1, spacing of 2. So wire width 0. Change my layer to T.U and start with my corners. So size A has a length of 3.2 and a width of 1.6, corresponding to that same EIA code. So length of 3.2 and a width of 1.6 translates to negative 1.6 by 0.8, negative 0.8. And I clearly have the wrong bend turned on. And positive 1.6, positive 0.8. Now I'm already unhappy with something here. I want to make this thing vertical. That's just kind of how I normally think of these caps. That's how the symbol is generally done. So let's do a quick rotation here. So I just did a group. Right, we talked a little bit about how we group, and then a move with a right click at the center, because remember, wherever I start clicking is going to be the origin of my thing. right-clicking, I want to move group, get back to the origin, and then I just right-click to rotate it. So now I'm happy again. Quick quality assurance, make sure that I'm happy, 3.2 by 1.6. Awesome. So now let's look at our S by F. Looks like E and F looks like they might be slightly different, but probably not. Yeah, see, E is a reference dimension, so I don't know what F is supposed to be. But that's going to dictate my SMD size. SMD, and the size of that is going to be, let's see, E is going to be my width, so that's going to be 1.3, and S is 0.8, it looks like. 0.8 plus 2. Okay, so I got a little room to maneuver on here. I'm going to make my SMD just a little wider because I do want that web. I don't want it to swim too terribly much though. And I want to make my S quite a bit longer, so I'm going to make that 1.2. Now, how did I pick those numbers? I don't know. I kind of made them up. Okay. I suppose I should do what I did before, which is the minimum gap here, G. I could lay that out and stuff like that. But I kind of know this chip pretty well, and I kind of know what I can get away with on it. So I'm going to give plenty of web on the outside there, and this time instead of calling them A and B, I'm going to use my apostrophe and call them plus and minus, corresponding to the names that I gave the other ones. Tick minus sets the name, and I had it as about here. Okay. Alright. Now let's do what I probably should have done in the first time, which is double check that gap. So I just picked a wire. I'm on the top layer, so I gotta remember to remove this. And I just drew a wire from tip to tip, and I have 1.4. Does that correspond to something compatible with the G? 1.1. So I got plenty of, I'm probably a little extra from what I need. So I would like to maybe make this thing 1.1, which means in the Z direction that's going to be 0.55 to, or the Y direction, 0.55. Okay, so that's where I actually should be on the gap. So, okay, I will move my pads just a little further in. What I was worried about is this is the no-go area, and S, I didn't want there to be a point where this area here on the bottom side of the terminal there had no copper. I'd rather there be a little extra copper and have to deal with that. So that's okay by me. So yeah, we're above that. So clearly these are going to stop somewhere on the edge in this gap between S and G's starting point. So I'm pretty happy with that. So let's make sure we remove. Okay. And we add our text label, which is going to be name. It's at 1.2. It's at the correct font. It's not quite big enough to fit in there, so we're going to have to drop him down. And now I get 1, 2, 3 characters worth of text inside there-ish. That should be good for this project. And last but not least, remember this is the documentation layer, so I got a couple different ways that I can draw that stuff, but I'm going to add some sort of marking onto my tdocu layer to show in the assembly drawing that this is the positive side, like that. Now that's kind of going to eat into my name a little bit, so now I've got the first character, second, and third. We might chop off the end just a little bit. I hope that no one will hate me for that. In the meantime, we have a nice thing. I suppose I could have made a poly that sort of wraps around it and something like that, you know, whatever. But this looks like the top of the chemet part, right? You know, so in the data sheet you see it's got like a little orange bar that indicates that there's a what's going on there. That's the positive terminal. So And you can good double check that that was the chamfered corner and that's the anode end, and I can see the chamfered edge there. So that's another good one. Just double check to make sure your parts have, when you say plus, you mean plus, right? So, okay, now we just got to do a little bit of silk screening. Wire, 0.127, 1.27, no, it's 0.127. There we go. Back onto the T-place layer. And remember, I want my ink to be well away from any copper. I had a happy little accident here. So let's get rid of that dealy bob there. And how am I going to handle this extra marking? You know, stuff like that. I could do a couple of different things, right? One of them is I could, and this is what I think I'm going to do. I'm going to stretch one end up a little bit, and I'm going to add a rectangular fill. So this is going to make a big blob of ink that goes right up to the edge of that thing. And now I have a silk screen mark, and heck, maybe we'll even add one of these over here too. What the heck? All right, silk screen is cheap. Try that again. I don't often use rectangles. I like polygons better. I find that they're more editable and a little bit more free to work with and stuff like that. But you know, it's a tool, and sometimes you use them, sometimes you don't. So, lastly, I didn't do this a lot last time, and I should have run my document. I think it's with a dash. Package program. Nope, couldn't find it. Run. Thinking about stuff. There it is. And now I've got a plus and a minus in a layer that I can always look at anytime I want. If I'm ever confused somewhere during the layout process, I can just turn on the pin names layer and see exactly where it was. So I didn't do that last time. I probably should have. So sorry about that. Okay, we finished our size A. Oh wait, we're missing our labeling on T-place. So back to where we're supposed to be. Correct font. And it does not actually matter where this is. Another option that I've done is I've put text labels next to things or in silkscreen that have little pluses and stuff like that. You know, it's just whatever floats your boat that day. So, and you may be wondering why I was worried so much about avoiding avoiding copper or avoiding silkscreen over these copper pads. And then I just covered it up, right? Aren't I going to apply when we go to do routing, aren't we going to simply do a copper trace coming in and out, right? This is going to connect the stuff. That's copper coming in this direction or that direction or whatever like that. And the answer is we're not seeing all the layers that are going on right now. There's another layer called mask that I'm going to turn on. If I can find it. Come here. Sorry, T-stop is actually what it's called. We refer to it as the mask, but Eagle calls it the stop layer. What this is it's a, and I already see that I have a problem now. This is why I don't like using rectangles, because I can't slide them. This is an area where that green solder mask, that green LPI solder mask that you see on boards, that makes them green, or you can get it in red or black or blue or whatever you want. But you know, generally green. That mask is blocked off by this layer, and this comes free with every pad or SMD that you put down. So this will expose raw copper, so there will be none of that green stuff around there. Everything else, including traces that I route in and out of this pad, will be covered up. So this is bare copper so that solder paste can go on there. Any tracks coming in and out are going to be masked off with that green LPI before the ink is applied, before the solder mask ink is applied. So that's why I don't worry so much about that. And this is driving me so nuts that I'm going to go ahead and just kill my little cool design and replace it with a polygon. on the T-place layer. It's looking good. I'm going to make the width a little bit. Well, this is going south pretty fast. Let's see if this gives me the desired effect. If I'm going to do that, I'm going to have to do it a little thicker, a little further down, so that whoever's using this and assembling it, which usually ends up being me anyway, I got no one to blame but myself. So now when we look at it, it's okay. I may come back to that one. The alternative is to fatten it up, in which case we would do one of these. Now it's much wider and it's much more prominent that that's definitely the marked end. I like that. That's okay. So that's looking good. So there was size A for us. Alright, cool. Save. Let's do it all over again. New package. This is going to be called a cap polarized size D. Okay, and now I get to my size D stuff. And I see that I'm 7.3 by 1.3, so wire 0. Start out at 7.3. Well, 7.3 divided by 2. That's 3.5 plus 0.15. 3.65. Negative. But I got faked out by that one before. So I need to catch my length, my width. D is 4.3. 4.3 is 2.15. Alright, quality check. 4.3 wide, 4.3 wide, 7.3 tall, 7.3 tall. Cool. We're looking pretty good. Let's go ahead and not make the same mistake that we did last time, where we skipped out on the gap in the middle. Not really so concerned about the x ordinate, so we'll call it 0 this time, and it was G, which now I can't remember which column. ABC. Okay, I could have probably just done that. 3.5. So that's 1.75. Come on. No, it doesn't like commas. I've been using too many CAD programs lately. Okay, quality check. 3.5. Alright, so I've got to get my stuff to go in there. And my F dimension, ABCD, is 2.4 wide. So SMD, 2.4 wide by S plus some extra, ABCD, 1.3. Wow, that's tiny. 1.6. Yeah, so this is a little bit more normal, where you see it's not very wide. Okay, so the gap is effing huge on this thing. So I mean, wow. I'm gonna make this even bigger. 1.8. Because I want it to stick out the end a little bit. Sure, that looks good. Some of this is just eyeballing it. Yeah, I like the way you look. So this is going to be called my plus, and my minus. sure I got it centered. Yeah. I'm just looking at the x ordinate. Okay, cool. So now, text name. I can finally use the normal size font because you can see this guy's plenty big. And I can use my cool little rectangle tool that I said I didn't like using too terribly much, but now it doesn't bother me because I know I'm not going to do anything weird. So there's my documentation. Ooh, I need to change layers. Change layer to t.q. There you go. The dead giveaway on that one was the transparency, right? I should not have been able to. I should have been able to see through that just like I do now. But top is an opaque layer, so that's what happens there. So all right, that guy's looking good, and this is getting to be pretty standard for us. T-place. Two seven. And this guy, I've got plenty of meat now to make a nice, good-looking polygon. The other one was a little cramped because of the fact that it didn't have very much width left over. You know, the terminal was almost as wide as the entire thing, right? So it's hard to make that. But now I got all sorts of stuff, so I can do cool stuff like this. Alright, so now I got a nice, cool, good-looking fill. And then we got our text. Onto T-names. Correct size. Change the font. There we go. Alright, so a little description I think was in order. Right? Size. EIA size. It was 73. 43, right? 7343. Okay. Dunsky. Alright, let's start making some parts. Now, like I said before, I don't, in the previous thing, I do not generally build in manufacturer part numbers and stuff like that for these parts. The reason I don't do that is because there's just too damn many of them. So let's go ahead and begin. Because last time we already created our symbol for it, we're now ready to create a device. And that device will be cap polarized. I realized I was pointing at the wrong thing here. Let me get to the thing. I'll show you what I mean. Okay, so capacitor polarized, always going to have the same symbol. That's how we kind of decide whether or not to create new parts. If I can recycle a symbol, I don't generally I don't generally create a new part. I just create a new package and attach it to the same part. So that's going to be C for capacitor. The value will be used. Start with a new package, and the new package will be size A. Now, I already know a couple of things about this, right? This window kind of walks all over the screen on me. The dielectric, I will shorten to the word tantalum, or to tant for tantalum. And I know the size. Size is going to be size A. That's my terminology. Probably I should get in the habit of using the EIA sizes, but I don't. Voltage is voltage. I think last time I was giving it place markers of 16 volts, so we'll call that 16 volts. Really, I will change that as I need to go on the in the schematic world. And is there anybody else? Nope, that's it. Occasionally I will put prices on there that are kind of like budgetary prices, but they're not very accurate, right? So now, plus, plus, minus, minus, and that's why I gave those pins those names. When last time we created this, we created plus and minus pins. Okay. Now I can do another, whoops, darn it, caught me again. I'm so used to doing these things one at a time. The variant name is something that's only optional if you have one part. So only one part can be called variant nothing. After that, you have to start giving it names. So let's give it a name. Dash size A. Okay. So, cool. Now we'll do another one. This will be called size D. Alright. The wiring is pretty straightforward. And I have all new attributes again. Right, so dielectric cant, size D, voltage 16V. Okay, cool. So that takes care of another two capacitors. Let's go on to our aluminum electrolytic. These have actually a fair number of sizes to the point that I have not really picked some favorites. But because this has basically 4 on there and it doesn't have a size D, I'm just going to go from A to E. That's, you know, and I'm not going to make all 4 of them. I'm just going to make 2 of them, A and E. Okay, so let's make some parts. The package. And this is going to be C, pole, alum, size A. So this will be size A, parentheses, 4 by 5.4 millimeters. These don't have EIA codes like a lot of other stuff has. So, you know, let me make sure. There's something a little confusing about this layout here. Oh, that's dimension A. It's not size A. This shows you how much I actually work in, you know, electrolytic capacitors. So okay, and if anybody remembers how we rename a library, we rename it using the library menu followed by the rename. So I'm going to call it 4x 5.4. Sure. Now I want to try to recreate that cool looking little kind of house sort of shape. So I got a couple ways that I can do that, and we all start with wire 0. Okay, and dimension B by C is going to be our basic dimension. So 4.3 by 4.3. Huh. Alright, well, whatever. I'm in the wrong layer. .3 divided by 2 is 2.15. Negative 2.15. Negative 2.15. Since I don't have a spec on what the chamfer really is there, and I don't really care because it's not a critical dimension, I'm going to start it out as a square and then I'm going to trim the corners on it is what's going to happen. Except it helps if you're in millimeter mode. Whatever. There we go. Okay. Alright. Now, how exactly are we going to create this chamfer? Well, what we're going to do is we're going to move them in. And you know something interesting about move? The grid is set up finer than the actual corner, and yet it moves it by an integer amount. It doesn't snap to a thing. So I'm going to move it in by 2 ticks, which would be 1 whole millimeter. And then I'm going to use the bend command, which is or split they call it, which is a command that's very useful in layout. And I'm already not liking the decision that it has made to change my life. So, back out of the bend command. Maybe I'll have more luck on this side. Kind of. I've created the bend that I want. I'm going to have to go through and manually edit something. Or I can maybe make my grid smaller. I just need it to look kind of right. There we go. I just didn't have my grid where I wanted it to be. So I set that up because I knew that my outside dimensions were 2.15, so that's a grid spacing of 0.05. So, okay. I don't know, it kind of looks like what it's supposed to, right? And so, good. Text, name, I've thought for years about not being so anal retentive on my fonts, and I keep saying, no, I'm just going to keep being that guy. I like this font, but it doesn't lay out well in manufacturing environments, so can't use it. Something it's a little odd looking. 3.3 length on that side. Okay, I guess that is right. It just looked a little lopsided to me, but maybe it's just the way the font's going. So, more SMDs. And this time, the SMD width is this dimension h, and the length is dimension e, so h by e. H by e. So a width of 0.8, 0.8 by 1. Wow, that's a different length than I would have expected. 0.5. I don't know what this terminology is here, but I'm going to go ahead and, because I hate leaving copper like that, I'm just guessing that that's the range, and I need it to be as wide as it possibly can be. So now, 0.1, I'm gonna make it a little longer. I'm gonna make it 1.2 so that it hangs off the edge just a little bit, and these usually can get some good capillary action coming out the thing there. Oh no, you know what? I'm wrong. It's dimension A, not dimension E. E is the gap. Dimension A is 1.8, so I'm gonna make that 2. And now that's a little more like it. I'm used to those things being kind of long and sort of skinny. And E was the gap, and E is 1.0, which means each one of these squares I've got set up right now is 1 millimeter, right? So as long as I leave a half a square or more in each one, I'll be fine. So that looks, I want to make it a little longer. That looks pretty good. It's hanging off the end, which means it's going to have a nice big web on there. And this will be the plus lead right there. You can, if I zoom in, probably easier to see. There's the plus lead right there. So the plus lead is at the top of the house. So plus, and minus would obviously be the other guy. Okay, so we're all done with that. I'm ready to do my place in my routing dimension. And T-place, or not my routing, but my silk screen. And let's turn that stupid fine grid back down a little bit. 5. Okay, this is looking good. Run documents dash package. I bet you I forgot to do that last time. All right. I need my text name on the T-place layer. I don't know where I want to put this. Sure, looks good. Save. Everybody's happy. Everybody's happy. So that was our smaller capacitor, and now we'll make another one, which is a new package called C pol Plume 4x5.4. 4x5.4 was the original one, and then I'm going to pick another one. I don't know, I'll pick something in the middle here. 6.3 by 5.4. Something big. Oh, look at that, it did give me a layout. Yeah, well, not the super big one. 8 by 10. Sounds good. 8x10. That's gonna be some. I bet you get some big capacitors out of that. So B by C is 10.3 by 10.3. So I do my wire 0. (10.3) by 2 is 5, negative 5.15, 5.15. And then we do our bender trick. This is a big capacitor. I've just decided that this is really quite big. maybe I picked the biggest one to work with incorrectly. So our pad widths are going to be H, which is 1.1, by A, which is 3.2. So 1.1 by 3.2 but the gap E is going to be 4.5. That's a big gap. That's 2 full. There's 1.5. It's 3, 4.5. Make this just a little longer. Well, I'll name it later. Name plus. Okay. Text name. Add my silk screen. Get a little finer grid. And voila. Add this to our increasing repository of capacitors. So we're going to add the aluminum, which is going to be called dash AL4X5.4. Sure, why not? And wire it up. Attributes we know are going to be die. The size will be 4.5 by 4x 5.4. Voltage 16V, and that's it. Lastly, bigger package. We've misnamed it again. Okay, so simple description of polarized capacitor. Alright, so everybody is happy here. We now have a full complement of resistors and capacitors. And this is where we wanted to kind of end up. So I know that the last two have been a little bit boring in terms of making uninteresting or unexciting parts, but they're important ones. As we get into making connectors, they get a little more challenging, mostly in terms of what you want the CAD to do and things like that. But this was our base of everything that we've got going on. So now we can actually begin to do interesting schematic things, because we have a part, an actual integrated circuit to work with, which was a compressor, and then we have resistors and capacitors, and we have voltage and power supplies, and we have title blocks. So we can actually, next time we will start working on schematics of things. So with that, thanks a lot, and we'll see you next time.